Good morning, everybody. So we've reached the last day of this school. It's actually the last half day because there will only be 2 lectures this morning. And the first lecture today will be actually the last lecture in the lecture series by Satoshi Tsujimoto, which will be on epsilon by orthogonal Laurent polynomials.
Thank you so much. Thank you, Chairman. And today I'm talking about some variation of the box-on-board system. In my previous series of talk, I introduced some it's a non-autonomous Toda lattice and also Laurent chain, which both of them we introduced some corresponding box-on-board system. And actually today, this talk, my topics is related to also related to this activity. And actually, this object has been introduced by Fabio-Spitz and Professor Geftman at 2000 as elementary Toda orbits. In their paper, they introduced some very important object which can connect the Toda lattice and relativist Toda lattice. It means that the orthogonal polynomial and Laurent polynomial can be related by using this rather complicated orthogonal systems. And here I have to introduce some binary sequence, epsilon 0, epsilon 1, 2, 2, and these are binary things, 0, 1. And this binary sequence, the epsilon, defines or determines the type of bi-orthogonal Laurent polynomial. And further, the other sequence, nu and eta, defined through this epsilon. So nu, k, and eta k can be defined in this way. And by using these sequence, we can introduce some bi-orthogonality. So here, Pn is a standard nth degree of polynomial. Maybe it's monic case. And also the bi-orthogonal partner, Rmx. This is the Laurent polynomial. But slightly different with previous Laurent bi-orthogonal polynomial system. Here is an epsilon case. So epsilon can be, from the epsilon, we can define this new sequence. Nu is defined this one, but here, nu defined, so denotes the newly added degree in the Laurent polynomial, Rnx. If let's think about, take that as an example, epsilon, 1, 1, 0, 1, blah, blah, blah. And then from here, nu and eta is defined in this way. And in this case, nu denotes the newly added. It means that R0, this is constant, so this is always constant, 1. And R1 is first degree of R1, but in this case, from the epsilon 1, so here -1 is appear. And it means that the newly added degree, 1 over x appear in this R1 Laurent polynomial. And then next nu defines next addition of degree in R2. So here, x to the 1, just x. And then the definition is just also corresponding to from this new sequence. And so you see -2 is appear and 1 over x squared is appear. So blah, blah. So R4, R5, 6, all of them can be defined through the first epsilon defined. And in this case, okay, so just we will consider this type of bi-orthogonality relations. So between P and X and Rmx. So okay, let's see the corresponding recurrence relation and also matrix form. So you see, so epsilon is plus or 0 or 1. And I introduced some epsilon star, but this is just -1. So here, epsilon star is 0 or -1. And in this notation, we can introduce some 3-term recurrence relation for this epsilon bi-orthogonal function, bi-orthogonal polynomial Pn. And here, I can, if the epsilon is 0, then in this case, this term vanish. So in this case, just coincide with the standard orthogonal polynomial case, just 3-term, very normal 3-term recurrence relation for orthogonal polynomial. But if epsilon is 1, then this term is disappear. But on the other hand, on the other side, this term will be emerge as a newly appeared in the other side. And in this case, so epsilon we can freely choose. So just epsilon can be chosen as a selection of type of orthogonal polynomial system. And correspondingly, we can introduce some matrix form as in this form. So, so here some notation sub indices subscript gamma 0 gamma 1. So here this is just appear in this by subdiagonal elements. And if the all gamma 0 gamma 1 are all 0, then this is nothing but unit matrix, identity. And also, if 1, 1, 1 is happen, this is some bidiagonal, lower bidiagonal matrix will be appear. But we can choose 1 or 0 or 1. Then epsilon, so L epsilon is defined look this one, like this one. And epsilon star is the opposite one will be appear. So this is an example. So if we start from 1, 1, 0, 1, this is a previous example. And then epsilon star is just 0, 0, minus 1, 0 is happen. So if the one side is non-zero value happen, then the other side 0 should be appear. This is some a kind of some shift, some element will be appear in the other side. This is happen in this case. So in this case, the corresponding this epsilon three-term recurrence can be rewritten in terms of matrix form like this. So here 1, 1, 0, 1 means one non-zero term, non-zero element, and 0 element appear, and non-zero element appear. So this is a type of biorthogonal epsilon biorthogonal Laurent polynomial system. Okay, this is by choosing this epsilon sequence, we can express Toda case, standard orthogonal polynomial case, or Laurent polynomial case. Both of them is contained in this expression. And then more interesting situation happened that this epsilon biorthogonal Laurent polynomial, by using this epsilon biorthogonal Laurent polynomial, we can connect with orthogonal polynomial and Laurent polynomial through some transformation, which was just Faber-Smith and Professor Geftman introduced this transformation. It's quite nice. And then our motivation, our target is how to understand from the point of view of box-and-ball system. This is rather complicated, but it's still what's the meaning of epsilon extension can affect or can lead to the some box-and-ball system rule should be appear. So what's happened? Just let's see. Okay, in order to understand the completely, I mean, from the point of view of exact solutions, also we need to be consider. We can analyze from the by using the theory of orthogonal polynomial system. Slightly here we have to slightly modify the theory, but it's possible to introduce the determinant expression. It's not so difficult, and also here the Pnx should be from this biorthogonality relation. It's easy to express determinant expression like this. Here, nu0, nu1, nu2 is 0, 1, and 0. Previous example is 0, minus 1, and 1, 2, blah, blah, blah. That's situation. But we can arrange the rows by subscript numbers. So from some bottom, eta n minus 1, then plus 1, plus 1, 1, plus 1. In some sense, this is very close to the standard orthogonal polynomial expression in terms of some determinant. But here I want to, okay, maybe after that, so the element, all element depends on degree n. This is a quite big difference with standard orthogonal polynomial system. And also, Hanke determinant should be slightly shifted like this. Okay, so it means that we can obtain the eigenfunction and eigenvectors can be expressible by using the moments. And also, in order to introduce the finite version of this system. Here we fix the n binary, the length of binary sequence should be restricted by n, and then osmolarity relation also slightly diminished. The range should be restricted. And in this case, the corresponding linear functional is also written in this way. So of course, Wj expression is how to introduce Wj. This is also possible to express, but here I want to omit the detailed discussion. But anyway, the linear functional also have this type of Gauss quadrature formula expression exists. And then spectral transformation. This is almost a similar trick can be introduced. So here, linear spectral transformation can be introduced through these four type relations. So already here, I introduced the two type of spectral transformation. Here, the spectral parameter is just 0 or some shifted parameter. So already we know about why these four relations should be appear, because already we explained or mentioned that how these four transformations play some important role in the non-autonomous box and ball system. So size limit or speed limit just combined together. And then so here K and T. So the spectral transformation for time evolution direction K and also T has been introduced through this four relations. And then, of course, the minus ST should not be taken as a zero of a polynomial system. So this is the restriction upon shifted parameter. So, and also I can stress that this S of T can be chosen freely under these conditions. Okay, S is a free parameter. And then, so of course, already we have introduced this spectral transformation. So we just for save the, in order to calculate the compatibility condition, just we can express in terms of, by using the matrix expression. So it's, of course, it's a bit tedious notation, but here, basically, R, L1 inverse or L1 Tudor inverse, all of them are bidiagonal matrix. So the basic idea is all member should be had some this type of bidiagonal expression. This is some key ingredients. And then already we know of some spectral transformation, so it's easy to compute the compatibility condition. But there are four relations. So not only the compatibility condition is not one condition. So there are several conditions. So here I put some of them. So here kt plus 1 can be expanded like this one. Also the other expansion exists. And also the other one here is possible. And I have to say that this P capital N, so this notation is coming from the already previous talk. I introduced this notation, but this P sub capital N it just means the characteristic polynomial of corresponding matrix pencil. So here, characteristic polynomial should not be depends on T or S. So they will should be same as in the along the time evolution. So P and KT it can be disappear after taking some compatibility condition. Anyway, we have some relation, element-wise relation can be introduced. Okay, of course, it's a bit complicated. But the compatibility condition is it's not so difficult after getting this the matrix form expression. And here is the expression. And basically, we have two time evolution directions. And I took the one of them as a true discrete time evolution. Here, t, and the other k taken 0 or 1. So correspondingly, we introduce the dependent variable, which depends on only t and n. So k is fixed. Okay. And then we have obtained the corresponding non-autonomous discrete elementary. So I say that this is a discrete non-autonomous elementary Toda orbits. This is introduced. Can be easy. And then, of course, in order to also already, I want to also don't want to explain in detail, but as in the same manner, same situation happened in the non-autonomous Toda case, some subtraction free form can be rather easy to introduce. So here is the final expression for discrete elementary Toda. So here we have no subtraction. And also, I want to stress that this is already, I mean that the so-called, in my previous talk, we may call that modified non-autonomous Toda lattice. This is a corresponding one. And here is the minus sign doesn't happen. And also, it's for, but here, epsilon I to something to the epsilon I will appear. But this epsilon I is slightly strange in the expression. But just here, I introduce this expression to avoid the cases distinction will not be happen. So just for sake of space, I introduce this expression. And then under this expression, if we took the epsilon as 0, 0, 0, 0, all elements are 0, then this equation should be returned to our non-autonomous, actually modified discrete Toda lattice will be appear. And of course, indeed so. And then the other side, if we took the epsilon as a 1, 1, 1, 1, 1, 1, then this discrete system can be interpreted as a non-autonomous discrete relativistic Toda lattice will appear. Okay. And then we can easily to apply the ultra-discrete limit to this system. Okay. Okay. Thank you.
So could you show the one previous slide?
Sure. Mm-hmm.
Yes.
Is it?
So, okay, how could you explain again how to get the second 4 equations from the first one?
You mean from here to here?
Yeah.
It's, sorry, maybe I made some mistake, but just changing the dependent variables. For example, here is just transformed to the other side.
Yes. So,
sorry.
Uppercase, you have 2, sorry, 3
I see.
independent coordinate, I, K, and T. And the lower one, you only have T and I.
Yes, like this one.
K,
So
K
you
is
see.
0.
So I took the Q to the, yeah. And also maybe some typo has happened, ST and this should be coincide. But
Yes.
anyway, basically from here, we assuming the K should be fixed,
Yes.
0 or 1. So here I took the K equals 0, then this term can be, I just denoted, just deleting this one in case of tilde is happened. If tilde is happened, this will be just changed.
So K tilde T happens for K is 1.
Yes. So
Yes.
sorry, this rather confusing notation. But I don't want to increase the number of new dependent variables. Sorry.
Yeah.
But anyway, if we fix, just fix.
Okay,
No
fixed.
other operation at all.
I see. Thank you.
Sorry. Thank you so much. Just for pointing out. And then, of course, firstly, we introduced the two time evolution direction. But we took the one of them as a true discrete time variables. Of course, it's possible to the other one. So just your preference. It's no big difference. But here we want to introduce we want to obtain the some good box-sample system, which will be should be very interesting to look what's happened. And here I took this discrete variable. And anyway, from here we can apply the ultra-discrete limit to here. Oops, sorry. Sorry. Before applying this ultra-discrete limit, we check some exact solution for this one. So we want, of course, it's only possible to take the ultra-discrete limit. The value should be positive or always negative. Should be happen. So we better to check the solution. And then we know about PNX and also coefficient, how to express in terms of moments. And then this is our moments, so Pn, mu n. And we assuming some inequality like this. So basically x0 and x1 plays a role of eigenvalues of corresponding eigenvalue problem. So here is a generalized eigenvalue problem. And also for convergence, we are assuming the plus S of t also do not destroy the order. This is just assumption, but it's not crucial. But for checking the positivity, I assume this one. And then the tau function, this is a Hankel determinant with shifted one. We will be expressed in this way. So it's, of course, this is Hankel determinant, so it's easy to do. So you see, everything should be, if under these conditions, this should be positive. Then the other, okay, then the dependent variable Q and Q tilde and E and E tilde, all of them are ratio of this tau function. So from this expression, it's visible, almost trivial to check that the positivity of dependent variables. And then moreover, by using this our tau function expression, the convergence also easy to check. So Qi should be some of the eigenvalues, and also shifted one also same. And and E and E tilde can be 0. So I already told the definition of L. If E is all of them at 0, then identity matrix will appear. So this is the our time relation behavior. So R times L, so which was a three-diagonal matrix, which will be tends to the converts to the some upper triangle matrix, and then we can obtain the corresponding eigenvalues. This is the meaning of numerical algorithm from this setting. Okay, then now after checking the positivity of this system, it's we can introduce we can apply the ultra-discretization limit. And then, so this is almost same manner. And then this expression, possible, not so, it's almost straightforward. But also, okay, so the epsilon sequence can be treated or interpreted as 0 should be plus infinity, or 1 correspond to the 0. This is the ultra-discrete analog of epsilon, value of epsilon. But here also some non-ultra-discretized epsilon appear. Here also this expression can just for the avoid the cases distinction, just avoiding this situation. It doesn't not so essential, but I prefer this one. And then, so also, I don't want to go into in detail, but it's possible to prove that if we start from these initial values, then time evolution step also positivity should be guaranteed. It's proven. So from this setting, if the negative value happened, how to understand, it's a bit difficult to interpret in terms of box number sequence. And then after establishing these results, just checking what's the meaning of box number system or ultra-discrete system. So in order to interpret from the point of view of box number system, we will better to define E-1 T. So this, previously I also mentioned that Toda system, especially maybe the first talk, you a question to me, but that Toda system only defines some finite lattice. How about the other side, left-hand side, right-hand side? Especially the left-hand side is important to define the starting point, this finite system. So this value can be computed or calculated by introducing some additional equation. Here, we introduce E-1. So this equation doesn't appear in the original Toda system, but I put in order to calculate the starting point of the Toda chain. It's not so easy. It's not so difficult. So just we introduce. And then we can introduce K2i and K2i minus 1. This is just, you see, the how many counting, so addition, how many epsilon I, how many qi, just slightly different. But by using this K2i, it's possible to transform to the Toda expression to the standard box number system. So box number system, in our case, should be binary sequence should be appear. The previous one is E and Q are all some positive integers. So here, in order to transform it into the binary sequence, we introduce this type of transformation. It's more clear, I think. And then after that, this Ki can be interpreted as follows. So in this sense, QIT means the length of the I+1 block of consecutive balls at time t. And also EI of t denotes the number of empty boxes between two blocks of consecutive balls. So this is a standard interpretation for Toda's. Okay, this is the time evolution step by just calculating here. But it's not so easy to explain how, like Toda system, standard original box number system, or original Roland type box number system. So it's a bit complicated. So I put just write down the rules as easy as possible. Just okay. First, in this case, of course, here this epsilon sequence is very important. So epsilon define the type of binomial polynomial, but this epsilon also determine fixed some rule how evolve this. And then, we start from, so this is an example, but we have epsilon. In this case, 1, 0, 1, 0, 1, 0 happen. And then, so of course, the size of the storing, number of consecutive blocks are 6. So here, 1, 2, 3, 4, 5, 6 blocks. And then each of them, we assign the value of epsilon k to the case block. So it means that this block assigned to the 1. 1, 0, 1, 0, 1, 0. It's okay. And then divide it into the subsequence, just left boundary of one's blocks. So in this case, so we have a boundary here and here and here. So 0 and 1, 1, 1, this is a V, this only 0 is V0, and this subsequence is V1, and 1, 1, 0, 0, 1, 1, 1, 0, this is the V2 subsequence. It's okay. In case of a Laurent case, so every cut, but according to this epsilon, we can determine which division should be happened. And then we introduce some carrier from left to right. In some sense, basic rule is the same. But if this carrier moves from one subsequence to the other sequence, next sequence, we have introduced two special rules. Actually, this is two special rules. And this is the, so maybe yesterday I introduced the box and propositions for Laurent polynomial. In this case, some new ball and box are moved together to the next subsequence. But in this case, we have to separate this new creation of a new box and diminishing this box. So we have to separate. And okay, just
before you go ahead,
okay.
Could you remind us what was the rule for in the Laurent case for moving the ball and box to
yes,
the
yes,
next?
yes.
What was the rule again?
Yeah, just for example, in Laurent case, we will put some wall in front of the left boundary
Yes,
of ones,
yes.
and then just moved inside the.
And whatever is extra now goes to the
And
next.
then,
This
some
one.
ball just moved to here.
Thank you.
And also this one moved to here.
Yeah.
This is the Laurent box and ball system. But so this is how to say, some ball moved to the next subsequence. Then correspondingly, we have to create new box. So here, one ball and box just inserted. So then this box and ball has been removed in this setting. But in our newly introduced or extended version of Laurent, epsilon Laurent, we should have two special rules. And okay, just first, maybe it's not so difficult, but it's a bit complicated. So firstly, I want to read this rule. And special rule one is just before moving, so the carrier is just around here. So just after finishing some box ball working, then stop at some intermediate position of subsequence. And then the special rule one is before moving carrier within the subsequence, create new boxes equal to the number of balls on carrier. So here, some carrier happened, and some ball should be carrier. And so same number of box, it's an empty box, just created to the next subsequence after the right end boundary of consecutive ones. This is the special rule one.
The carrier is moving the wrong way.
Sorry?
Your carrier is moving the wrong way.
Oh, this one is wrong way here. Sorry. Okay, it's okay. And then this is the first one. So, and the special rule is, in substance, this is after moving the subsequence. But here is slightly different manner, but just also read. For the balls in the first blocks of ones, if you move them beyond the next block of ones or into the next 0-1 subsequence, in this case, remove the original box where the balls were placed. Yeah, you see, this ball beyond the next consecutive ones or moved into the next subsequence. In this case, this box should be removed. Okay, and so just Laurent polynomial case, Laurent BBS, just coincide, just join together, in one together, these two special rules. But in case of the epsilon, it's a epsilon BBS, epsilon BBS will be introduced in this way. And then let's also, okay, let's slightly complicate. I can, okay, just for explain by orally. So here we have divided into subsequence, this one, this one, this one. And then just 0, 0, 0 is how many number of balls appear on the carrier. And also S of T is here is the carrier capacity. I also introduce. Sorry, it's very complicated. So we have some 3 boxes can be loaded into the carrier and then moved here. So catch up, catch up, catch up, and here unloaded 1 ball. And so carrier only 2 balls loaded. And then the other, so in the subsequence, a carrier play almost same, just pick up, but this one is already, capacity has exceeded, so this one should be untouched, just nothing to do. So 1, 1, 1 here, and unloaded, but still 1 ball remains. So this one, 1 ball has been carried over to the next subsequence. And yeah, also we can check after moving this carrier, we know about these 2 balls has been jumped into the other, jumped over the other one, consecutive one. So this box should be removed. And then finally we obtain the 0, 1, 0, 1, 1, 1, 0, 1, 0, 1, 1, 1. Okay.
I did not understand the last point.
Yeah.
But these balls are going into the same subsequence, right?
Yes, subsequence, but that's beyond the next consecutive ones. Only between this first block and the second block, so only allowed to
only one
ball can be allowed.
Yes. Okay.
But the rest of 2 balls has been beyond more jump. Okay. So in this case, corresponding box should be removed. This is that I just. This is the rule. So, and here I want to point it out that the length of subsequence could be reduced or not same. And then, of course, and yes, here 1 has been appeared. So it means that we need to put 1 more empty box here. So in this case, I wrote down in some special arrow. So this is double arrow up here. In this case, some new empty box has been inserted before carrier has been removed. And then, so you see from 1, 1, 1, but here we unloaded 1 ball to the newly inserted empty box. So here, new 1 will appear, and the rest of carrier, only 1 ball has been remained. From here to here, 2 balls has been unloaded. This is the meaning. Okay? Okay, this is the most complicated part. After that, this is not so. And then just go down, and then 1 ball has been carried out. So this one goes then. And in this case, no ball has been exceeded to jump to the next consecutive blocks. So no removal doesn't happen. And then the rest was also same one. And this one has been overloaded, carried over. Then some empty box should be inserted to here. And then just go through the same way. Okay.
I'm sorry,
yes.
I have a question. I forgot the carrier capacity. What does it correspond to in the discrete system? It must be the ultra-discrete limit of something.
Yes.
What is it the limit of? Could you show the slide with the ultra-discrete limits again? Where does it come from? S?
Okay. I just show you. So this is the spectral transformation.
Yes.
So this S of t. So in each step, in each time evolution step, actually, at this moment, not time evolution. This is a spectral transformation for also the polynomial system. So here we can introduce the some arbitrary parameter can be introduced. Of course, I already pointed out this assumption should be.
Of course.
But basically, S of t can be chosen as a freely in each time step. And this is the, which leads to the carrier capacity of each time.
Okay, I see.
Yes, this is always, in every step, we can choose this parameter S of t because of the orientation originally is coming from this parameter. And then, yes, and then now we slightly complicated, but it's possible to explain both of them, box ensemble system and this Laurent type box ensemble system simultaneously within by using this special some additional two special rules. Okay, and then so of course I'd better to say one more comment on the relativistic Toda box ensemble system. So previously I mentioned that if epsilon takes all elements are ones, then which correspond to the Laurent polynomial. But here we can choose 0, also possible. The same system can be achieved. This is because of the property of epsilon Laurent biorthogonal polynomial. So I think that Professor gave me why this situation happened. But from the initial, it's a bit strange. Feeling such situation we may happen. And it means, so also I tell you that this epsilon defines the rule of box ensemble system. So here, if we took the different type of epsilon, the rule also should be changed. Yes, should be changed. But in this case, so this final epsilon means insertion or not. This insertion doesn't happen or not. It's the final result will not be changed. The same result could be obtained because of the left-hand side, right-hand side. We have infinitely many zeros happen. So the newly created empty box will not so essential. So we can explain this Laurent box ensemble system from this 11110 rules. Same result could be obtained. This is a feature of epsilon LBP or epsilon BBS case. And also, yeah, also I can actually the extension is not stop at this moment. I mean, we can also extend this already complicated big box ensemble system to the colored system. And this is epsilon D biorthogonal. I just sketch the outline. I just want to say which kind of difference appear in the orthogonal relations. This is the most important part. So here we can introduce the biorthogonality. So monomial, usually previous epsilon biorthogonal Laurent is just Pnx and Rmx. But this is so-called D-orthogonality is some discussion or we know about such D-orthogonality appear in the standard orthogonal polynomial system. So here we also introduce a similar extension of biorthogonality. So x to the d. So starting from this biorthogonality relation, we will obtain the some d plus 2 epsilon type d plus 2 term recurrence relation will be obtained. And the matrix form I also don't want to go into there, but matrix form also some lower bidiagonal and multiplication of upper two diagonal matrix. So it means that bandit, not three diagonal. So D plus 2 bandit matrix pencil will be achieved in this case. And then, analogously, I also just showing the just outline the corresponding Christoph transformation, Jerome transformation. In this case, slightly changed. So here, T plus D appear. So previous one is T plus 1. In this case, in our case, we can introduce this one. And compatibility condition and blah, 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 just repeat it. And then this is already too complicated, but the rule, colored rule is rather simple. If we know about epsilon, original epsilon BPS. So just composition. So we have a D type of balls. So I mean D number of colors are D, and such a colored ball, D types of ball has been introduced. And then, so time evolution step is first just divided into the several steps. And the first one is just starting from the type 1 balls and the color 1. And then, so the balls of color K just compute the time evolution as in the epsilon BBS. So no other ball exists besides those of the color K. So just neglected the other colors. And then next step is, so if starting from K equal 1, and the next one is K equal 2, K equal 4, and up to the D, just repeat. After finishing this repeating procedure, this rule, applying these rules, then one time step evolution has been finished. This is the color version of epsilon BBS. And in this case, yeah, of course, I don't want to compute, but anyway, here is the expression for colored box envelope system. So if we changing the color, the epsilon, if we even start from the same initial value, the final result could be changed. Of course, should be so. This is happen. So this is some extension of epsilon BBS, and actually more extension also possible. But also I don't want to go further discussions at all. Okay, and this is the corresponding BBS. I mean the new extended box envelope systems related to the Professor Geftman's elementary Toda orbits. Actually, it is. And then also I want to. It's rather complicated. I introduce some rather complicated version, but this is a bit more simpler extension has been done in terms of R1 type bi-orthogonal polynomial. This is also very well known in the theory of classical orthogonal polynomial system. And this is also possible to consider as some extension of Laurent polynomial. So here also, we don't introduce epsilon extension, only the Laurent can be extended to the R1 type. And in this case, some polynomial system can be, has some orthogonal with some rational function. So here, we can introduce some pole, kappa j. And kappa j is a prescribed poles. It means that the previous Laurent polynomial case, only pole has happened in the 0 origin. But in our case, the pole can be chosen as a prescribed poles. And from this system, we will obtain some also some recurrence, 3-term recurrence, but with not standard 3-term recurrence. So one of them is tridiagonal, the other one is bidiagonal. So these matrix pencil should be appear. And maybe it's better to think we compare with previous matrix form. In that case, bidiagonal or almost tri-diagonal, but with some deficit. If V2, in case of epsilon case, V2, if this term element are 0, then correspondingly this element should be non-zero happen. But in this case, basically full tri-diagonal matrix appear, and also the other side also full bidiagonal matrix should be appear. And then also, I don't want to repeat, but just I would like to express that as a moments expression. Also possible to write down explicitly. And then determinant expression for Pn is written in this way. And this is same as previously. The moment, so in this determinant expression, each element should be depend on degree of n. This is a difference with standard orthonormal system. And moment has some slightly complicated linear relation. So here we have two indices in the in the moment, but these two indices not independent. So they are related with this type of relations. It's a bit okay. And then in this case, already established some spectral transformation for this. And then also I just skip. And the compatibility shows us some discrete system, and it's also possible to introduce some subtraction freeform, this one. And then we also apply, we can apply, also I omit the discussion on exact solution, some solutions. Also we can check the positivity of these dependent variables. And then this is the, also I omit some non-autonomous parameter, but here some simpler version. And then you see this is ultra-discrete R1 chain. And also it's Kn is coming from the parameter of prescribed poles. And if this prescribed poles has been is less than this ENT, if such situation happen, this system should be reduces to our well-known non-autonomous ultra-discrete Toda lattice. So in some sense, this is a very natural extension of Toda system. And then, okay, sure.
Sorry, could you go back to the previous slide, please? Because you said it's subtraction free, but that's only true if there's some condition on the previous slide.
Okay, so wait.
Subtraction-free form. Yes, but that's only true if there's some relation between the parameters and the poles. Mm-hmm. Yes. Well, what do you do there? You impose positivity for the coefficient.
You mean?
Yes. Yes.
Okay. In this case, mu t should be taken non-positive values.
Okay, that's how you solve the problem.
Yes.
Okay.
Yes. Thank you. Of course, otherwise impossible. Yes. Of course, I omit some detail, but under some appropriate conditions, it's possible to take ultra-discrete limit. And then we can check what's the meaning of kappa. It's also very interesting to see. And then this is our interpretation of this model. So this is, maybe I can say that this is a slide system. So this 6 and 5 are our prescribed pole, coming from the prescribed poles. So not all some consecutive one blocks. So each blocks, but the first block doesn't contain this some integer value. But here, this second block and third block has some non-integer value, 6 and 5. And 6 and 5 means how many number of boxes has been slide system can be applied. So here 6 means this the left hand side 6 1 2 3 4 5 6, until 6 boxes. If some ball has entered into this range of empty box, this ball can be put into the second blocks. So here you see also 5. So the third block has 5 integer, and this 5 means 5. Let's consider the 5 empty 5 boxes at the left-hand side, and in this range, some 2 ball has been inserted. It has been appeared, and then these 2 balls have been pulling to the third blocks. This is the first step. And then after this, we say that slides, after applying this slide system, then the last step is just applying the same rule as in the box and ball system, the standard box and ball system. And then this second 2-step, after finishing this 2-step, we achieve we think that this is a one-time step evolutions. And then here is the how this.
Sorry, I'm a bit confused. So this whole thing is one move, or these are 2 moves? 2 time steps or one time?
No, one-time steps.
One-time step. Okay, and then I don't understand the second step here. So this 060, I mean the second block, in your second block.
Yes.
When you do the moves, the 6 should go in the middle.
Oh, but okay, sorry, yes. I thank you so much. And 6 is not assigned to the ball, just block.
Ah, I see.
Sorry.
So it always goes to the left
just
of the...
shifted to the last ball. So this 6 assigned to the, not the each box. Yes, oh, yeah. It is the block. And then...
sorry, and another question. Okay. So you had said that earlier your pole locations were arbitrary real numbers.
Of course, some non-negativity or non-positivity has been assumed.
Yeah, but at least real.
The rest is...
So are you assuming the poles are integers here? Or
sorry?
Are you assuming that the poles were integers in this example?
In this setting, I assuming integer.
Okay, so if it's some real number, then you go half.
Of course, it's very important. I want to check. Yeah, it's also, and I'm checking.
What if the number of a block is larger than the size of the 2 previous blocks? Okay. What happens?
Yes. Such situation may happen, but if we start from this appropriate setting, if initial condition, then the rest should be same situation happen. This is the theorem. You see, always if if the initial condition satisfy this condition, though this is just this slide doesn't go further, doesn't happen. And then you see if the initial condition this setting this condition satisfy, then the further always positive. So this. Of course, it's, thank you so much. This is a very important feature of this system. And you see, so like this, maybe this is some other example which are starting from a Toda system and the Laurent system and the R1. And also we can introduce, in this case also maybe epsilon extension can be done, but at this moment we can say nothing to do. And also, sorry, I have to finish. And I completely omit these related topics, but I just pointed at one comment that so previously, I mean, the discrete system computes the eigenvalues of corresponding matrix. This is the discrete system in our Toda, finite Toda computes such situation. But how about the box and ball system? Of course, there are already some understanding from the point of view of numerical system. And so this is, of course, the BBS system itself, a kind of sorting algorithm. This is done by Nagai-san, Takai-san, Tokihiro-sensei. And also some ultra-discrete analog of maximum eigenvalues of max. This is possible to compute by using the ultra-discrete Toda or something. But now the other interpretation can be done that our Toda box and ball system can compute the invariant factors of integer bidiagonal matrices. So someone maybe you know very well on the some Smith normal form for integer matrices. And in this case, of course, this is the form of Smith normal form starting from the integer matrix. And by applying the integer matrix GL and Z, and by applying this P and Q from left or right, and then we can always, it's possible to obtain some this form. It's a normal form, and R1, R2 are all integer, and R1 divide R2, R2 divide R3, blah blah blah. And then 0, 0, 0 appear. And here, these R1, R2, or RK is very important in the, of course, make some Jordan blocks or some homology groups. So sometimes. It's possible to compute this integer bidiagonal matrix case. So of course, we start from this one, this integer matrix, and then our ultra-discrete Toda can be converted into the so-called GCD Toda. So you see that in case of the minimum operation can be expressed in terms of GCD from this expression. By introducing this relation, so in some sense, UD to ultra-discrete this expression and GCD type version of Toda is not exactly the same. Actually, it's possible. This one, GCD Toda, has correction of ultra-discrete Toda. The meaning of it's not so. It takes some 1 more 2 minutes. But anyway, we can say that starting from by using this GCD Toda can be performed this some computation, and then we can obtain after some computation we can obtain this Smith normal form or invariant factor of corresponding integer matrix. And the proof is not so difficult, and we use some conserved quantity of ultra-discrete Toda or ultra-discrete boxable system, or also this division property also possible to easy to explain that so the property of boxable system if we know. And then this is a final slide in my talk that computation is really possible. This our boxable system can compute the Smith normal form of this corresponding integer matrix. Okay, this is my last slide of my talk. Thank you so much.
Thank you very much. There's still ample time for questions or comments. Yes, please.
Thank you. So in this R1 example, when you define orthogonal polynomials, defining the German formula is no longer Hankel, right?
Yeah, it's in some sense it's possible to transform.
Yeah,
it.
but since it doesn't look Hankel, so it has this feeling like you're dealing with bi-orthogonal polynomial, which is more related to 2D Toda. So maybe you can do some similar discretization, ultra-discretization for 2D Toda.
Yes. Yeah, I think yeah, it's possible, but of course, it's very the setting of initial condition is not so. It's possible to do, but we want to analyze some generic behavior. But at this moment, I have not yet done for 2D case.
Any other questions, comments?
So I'd like to ask you about lowland Toda system, where epsilon is epsilon is 1.
Okay. 1, 1, 1, 1.
Yes, and in that case, sometimes a box with ball disappeared, so erased in the procedure.
You mean that
in the exam, maybe not the lowland case.
Maybe I think that you mentioned that epsilon BBS case.
Yes, maybe.
And of course, I forgot to mention about notice remark that such situation happened. that you see, this is a U0, and we divide it into V0, V1, V2, V3. But after applying our rule, we obtain V0 prime, V1 prime, V2 prime, V3 prime. If we consider concatenation of this sequence, the length should be not same as before, as a subsequence. Of course, if we consider the infinitely many number of subsequence, it doesn't matter, but as a, you see, the
So sequence, you mean the number of balls?
Yeah, number of balls.
Balls. Oh, so I thought from your explanation that some ball with box is erased in the
No, I don't think so.
procedure?
Maybe if such situation happens, it's maybe it's okay.
One ball.
Carried over to here, and then go insert it. And this
I
one
see.
carried over to here and go down to here.
So the number of balls
Should be
is
reserved. Reserved.
Oh,
yeah.
I see. So I misunderstood.
Sorry, I
Sorry.
was thinking about the length of subsequence. Not some empty box could be changed.
I see.
Number ball. Yeah. So the ball should be visible.
Maybe this question is stupid, but so you showed that if you insert these prescribed poles, they act like some sorts of attractors, right? They pull the balls from the previous block to the block in which they are assigned. Is it possible to insert zeros instead of poles, and they would have a different effect, or?
Sorry, I mean here is.
Yeah, no, I meant in your definition, right? You put poles under the orthogonality condition of polynomials, you insert those poles.
Mm-hmm.
How about instead of putting it in the denominator, you put it in numerator, like you put zeros instead of poles?
Maybe it's impossible to introduce. Actually,
I don't know.
maybe.
It
Sorry,
feels
I try to forget about the detail, but yeah, you see, you mean the orthogonality?
Yeah, exactly. In this definition on orthogonality.
Yeah, so
Like
it's not allowed to. Yeah, maybe it's not allowed to same as a join coincide with denominator and numerator zeros. It's not so. It's not allowed. So
I actually have a question very close to what Inoue-san was asking. I don't doubt that these are integrable systems, but what about conservation laws? Because you have very exotic evolution rules. And of course, the ball number is conserved. And what about other conservation laws? Do you have any?
you mean R1?
Yes, but these are integrable systems. So what are the other conservation laws? It's not only the number of balls that is conserved. There must be plenty of conservation laws.
Okay.
Where are they? Do you have any idea?
Yeah. At this moment, I have no idea. But by using this matrix expression for this system, it allows us, we can put some spectral parameter inserted here. I hope, I may be almost sure that it should be possible. But at this moment, I haven't done that.
But if you go that route, then to me, it's not clear how you would actually solve Cauchy problems for this. You should be able to define the conservation laws on a given initial condition and not have to go through some matrix factorization problem.
Okay,
Well,
so in some sense, okay, you mean that in case of the Laurent case or epsilon case, we have some shift or okay, phase shift. Sorry. So just sorry. I missed position. Yeah, you see the Wj. This is the conservation. So of course lambda j and lambda j is the length. So each number of the size of solitons. This is correspondingly eigenvalues. And this is Wj. This is a weight of also in this orthogonal system. So, and this Wj is conserved. So this is the other conserved quantity in this case. So here we know about the corresponding expression for Wj. So I'm almost sure that should be, again, a conserved quantity. But of course, we have to be careful after applying ultra discrete limit. Sometimes independent conserved quantity will not be independent. So we have to be careful. But basically, it's okay.
Any other questions, comments? If not, then let's thank the speaker again for his very nice lectures. Not only
Thank you so much.